Sometimes the ray diagrams don't quite make it clear exactly how far and big an image is. Instead, we have a mirror equation where we actually know all this information. Usually we'll know two pieces and we can find the third, but it doesn't matter which one it is. Here, f is the focal distance dependent on the mirror, do is the distance from the object to the mirror, and di is the distance from the image to the mirror. Now we have some conventions for positive and negative signs for each of these terms that you'll need to know. First, the focal length is positive for concave mirrors and negative for convex mirrors. Second, the object distance is positive if it's a real object or negative if it's a virtual object. In most cases where we're working with one mirror, you'll only use a positive value for do, but with more complex systems, sometimes you'll end up with an actual virtual object. Lastly, the image distance is real if the lights actually converge, and virtual if the light rays do not converge. So if you see in your diagram that you have dashed lines converging, that's when you have a negative di. We can also determine the magnification of our system from the size of the image over the object size just by this equation, where di is again the image distance and do is the object distance. Here we have two more sign conventions. A positive magnification means you have the same orientation as the object, which you can see here. A negative magnification is when it's upside down. Now try to work through examples using both ray diagrams and mirror equations. They're 100% consistent and should give the same answer if you keep track of your principal rays exactly and your positive and negative values.